in the NADH, right? What else was there in the NADH? What else? The H plus. So when you break down the NADH, you're not only releasing your electrons in green, but you're releasing your H's, which I'll show in brown. So you're releasing your H's to the outside. What are you creating with the more addition or the greater addition of H pluses? If you bring all these H pluses to the outside,
more potential energies are going to be changed.
do what?
Like more potential energies are going to be transmitted.
Right, so you are creating the electrochemical gradient. As you bring all these H pluses out here, they're building up in huge amount. Cool? Okay. Now, of course, we know the rest of this story. Your H pluses are going to come inside, right? Down their electrochemical gradient. What are you going to make from that? ATP. That means that this is what enzyme that I've seen, you're seeing right here. ATP synthase. Is this oxidative or substrate level phosphorylation? Do what? Oxidative, very good. And let's explore why that's considered oxidative now. What type of reaction is this right here as you're taking your NADH and making it into NAD+? This is an oxidative reaction, right? This is oxidation as well. So because of the oxidation of NADH, you can make this ATP. And this is why it's called oxidative phosphorylation. So do you see what's happening? You are pushing out all of your H's, pushing your electrons through this transport chain. The H's fall back through, forming ATP. Now you have NAD plus again, and FAD. What can happen to those two guys? They're reused. Reused later on. Recharge them. You're like, where would I do that at? Glycolysis and Krebs. You're recharging them. You're making more NADH. You will continue to break down food. Okay. Now the one thing we haven't mentioned is exactly what's at the end of this arrow. Where do the electrons go? Well, from chemistry, you know that electrons will always go, they will gravitate towards something that is very electronegative. Something that wants electrons very badly. Electrons go to where they feel the most love. The one chemical out of all this mix that we haven't talked about yet is one central molecule that has a high electronegativity if you look at its atoms. Remember that this is respiration C6H12O6 plus 6O2 to produce 6CO2 and 6H2O. And we really haven't talked a lot about yet the using of the O2 and the making of H2O. We have talked about making the CO2, right? I've even counted all 6 of them for you. I did that yesterday and a little bit the day before. We've talked about breaking down glucose. You've been here. So now we need to involve the O2 and the H2O. And here's what it is. The electrons gravitate towards the electronegative oxygen. In fact, a key statement to make right through here is that oxygen is the final electron acceptor. Till the end of time, I promise you this. This will be on your AP exam. This is an AP exam question. What's the final electron acceptor in respiration? That's pretty obvious. Oxygen is. Now, what does that make oxygen if it's accepting electrons? Does oxygen become negative or positive? Yeah, because electrons are negative. What is negative like? Something else negative or something else positive? Positive. Negative and positive attract, right? Do I have a positive member that's around? The H plus is just falling back down. So what's going to happen with your H plus? Well, it's going to find your O2 that's negative. And what do you make from that? Your H2O. That's your final product of the day. The formation of water. Cool? What do we think? Very doable. Okay. So let's treat this right here as a review, because that's really what this is. This is a review. I'll give you just a second to copy this down. You can really what I'm looking for is the boxes. This one box outside of the mitochondria. This circle, which is inside the mitochondria. And this last box over here. And your three major reactions real quick. Right? And you blow off the first of several what? CO2s. In fact, you blow the remaining 4 of those CO2s in the Krebs cycle, right? And you know the Krebs cycle is not just responsible for making more NADH, it makes like 6 NADHs, but it also makes 2 FADH2s. And again, you'll notice that all those NADHs and FADH2s are all being sent down to your last box here. So what is your last, before I go forward, I'll come back to that. What is that last box? 2 really events if you think about it. The first was the electron transport chain. Right. Chemiosmosis and the ATP synthase was being used there. Okay. And what were you doing to all of your NADHs and FADH2s at that time? Ooh. You were doing oxidation. Taking all of your FADH2. This would be an oxidation reaction. Cool? Now remember that along the way, you've been generating energy. How many ATP did we make at this point? 2 ATP. How about how many ATP here? 2? 1 for each pyruvate or acetyl-CoA. What type of ATP production was that? Was that oxidative or substrate level? Okay. And then here, you didn't make just 2 or 4. You made a lot. You made probably about 34 ATP. And this would be called oxidative phosphorylation. What are we thinking? Good? Manageable? Yes, sir.
Just go like where I'm just confused with where all left the 34 ATP come from at that point.
Like where they are all coming from?
Yeah, I just did a lot out of nowhere.
Let's go back to this drawing real quick. The reality is that for every NADH, you actually can make, and this is a very approximate number, because as you could guess, this rotor, this turbine situation, or whatever you want to call this, it doesn't turn exactly an integer number. You know what an integer is, right? Basically a whole number. It doesn't turn a whole number of times for each NADH. It's like for each NADH, and I'm going to be a little off here, and it's honestly different for each person, but each NADH causes like about 2.7 turns, which means you can make about 2.7 ATP. And each FADH2 that's broken down can cause like a 2.4 ATP, something along those lines. Well, let's think about some of the logic here. You made 2 NADHs from glycolysis, right? You made another 2 from the shunt, right? And then you made like a total of, what was it, 6 in the Krebs cycle, right? So 4, now you got 10. 10 NADHs. Well, I've got 10 of those guys. And remember, I made like 2 FADH2, right? That's about 27 and about 2.4, right? So that's going to be, or no, 2.4, that's 4.8. That's going to be 32, 33 in the realm right there if you do the multiplication of 10 times 2.7 and 2 times 2.4. So, I mean, that's where you're getting the approximate 34 ATP. And honestly, I don't remember the numbers, and your book doesn't use the numbers, but so they're going to be slightly off. It might be